talk at IST Austria. Anna, can you go ahead and share your screen? And she'll be speaking about controller synthesis.
Hey, I hope you can hear me.
Yes.
Okay. Thanks, Sanjay, for introduction. And thanks, previous speakers. Basically, you already introduced all the motivation, so that doesn't require me to introduce that. I will be talking about controller synthesis, and in particular, how we are trying to combine controller design with machine learning, how to take advantage from both worlds. And since there has been already shown a lot of examples where machine learning can be used for robotics, machine learning can be used for self-driving cars and many other applications for perception, neural networks can be used as well. And where is the controller synthesis that we are talking about? So we have a controller here and we have a plant. So the controller communicates with a plant. And plant can be in a certain physical state at every point in time. So this state is read by the controller. And then the controller has its goal to choose a proper action for the plant to continue to its next state in the next point in time. So this can be also done using, for example, deep reinforcement learning. If our specification is a very difficult optimization problem, or our state space is huge and formal control synthesis cannot deal with that, then what deep reinforcement learning will have as a goal is to maximize expected rewards. So now at each point in time, the plant is in a certain state, and then the controller for each its action receives a reward from the plant. So this kind of controller using, let's say, deep reinforcement learning can be synthesized offline. But then it's deployed, and then online, the system can be in a certain state which agent has never seen during training. So let's say we synthesized everything, we produced a nice controller and we deployed it, and now the agent runs into a state has never seen that state. So what is the agent supposed to do in this case? And this is exactly what motivates our problem. This is what motivates to investigate how formal methods can help machine learning, or in this case, deep reinforcement learning, to be not only well-performing and maximizing expected rewards, but also to be correct by design and avoid such situations. So if you would like to learn a little bit more about how to synthesize controllers for very complex optimization objective based on optimization, then I would recommend this works that were also done together with Rado Grosse, where we in particular investigated cyber-physical systems and how to synthesize controllers for them to achieve a certain goal while avoiding unsafe behavior, and also how to prevent the system from being a victim of adversarial attacks and how to direct the system to safety. But in this talk, I would like to focus on these two works done together with my colleagues from IST, Tom Hensinger, Christian Schilin, and also Guy Avni, and the student that interned with us. And first, I will talk about formal methods with a touch of magic, a bit in detail. And then briefly, I will outline our work, how we detect novel behavior in a neural network using abstraction taken from formal methods. So let's see. The first work, we call it with a touch of magic because we consider the product of what deep reinforcement learning does sort of magic for us, because it does something that is a black box for us and it does not explain its actions. So we know that deep reinforcement learning optimizes performance. If we take reactive synthesis, for example, as we've seen, what reactive synthesis does, it takes as given specification, for example, in certain logic, and then the goal of reactive synthesis is to find a controller that ensures that the physical plant satisfies this specification. no matter what happens. You can already see that reactive synthesis in its classical form, classical formulation, does not take performance into account. While deep reinforcement learning cannot account for the worst case scenario, does not provide worst case guarantees. Ideally, we would like to have a model that we would extract from deep reinforcement learning, give it to reactive synthesis, and ask reactive synthesis to follow this model as closely as possible so that we could also account for performance while synthesizing a correct controller. However, the problem here is that the model that deep reinforcement learning outputs is a neural network, and they are large and uninterpretable for formal methods to deal with them. Instead, we propose to use what we call a magic book. So a certain magic behind deep reinforcement learning would be approximated by another model that closely approximates the performance of the original agent, but it is small enough for formal methods to deal with it, and it is also more interpretable. Then this magic book can be given to reactive synthesis, and reactive synthesis would follow the magic book as closely as possible when choosing the actions for the controller. So this is briefly what the framework does. And an example of such magic book could be a decision tree. Well, in our work that I'm presenting here, published in FMCAD last year, we found that random forest gave the best performance for this task that we designed here. So let's see a little bit more in detail based on the example. So let's say that we had our deep reinforcement learning agent, which we also call a wizard because there is some magic behind it. So let's say we have our wizard. How do we get a magic book out of the wizard? Well, we observe what the wizard does, and we collect so-called state action pairs. So for each state that we see the wizard in, we collect what action the wizard does. Then we collect many of those. I don't know, maybe thousands of those. This gives us a training data. This data we can use to train, well, let's say for simplicity, a single decision tree. And this decision tree would tell us for each predicate on the state, what kind of action the agent approximately would take. Let's say that there are certain actions here. And now what we can do with this model, now we have this model here, we can verify it, for example. We can use bounded model checking to verify certain properties of this decision tree. And here's an example of such property. Let's say we have a taxi on the grid. So taxi is here. Let's highlight it a little bit. So this is our taxi here. And on this grid, the taxi needs to collect passengers. And the property here that the taxi never runs into a loop. So we define our state. Our state is the position of the taxi on the grid. So this is our taxi. And all the positions of, in this case, 2 passengers on the same grid. These are our passengers. So when the passenger is collected, a new passenger appears at random point on the grid. And now what we would like to do, we would like to write down this property as constraints. So the constraint for the loop would be that our taxi runs into, after several, let's say, L steps, into the same position as it was before. And for also Y coordinates. And then the same we have to do for passengers, but in this case, the passengers for a certain number of steps do not move from their positions. So basically, none of them was collected. So let's say this is our J to K. And for a certain number of steps, we say that our passengers stay in the same position. Here's why. Okay. So writing down the property like this, we can use bounded model checking to check if this, if there is a counterexample. Okay, so we've done that. Now we are sure that our magic book is checked. So we have it, oops, sorry. So we have it here again. This is our decision tree. Let's say. And there's a certain action. Well, let's put it here. So now we would like to synthesize a correct by design control. So how can we do that? We design a game on an MDP, on the markov decision process. We have two players in this game. The first player is us, the controller, and we would like to win, of course. And then the second player is the environment, the adversary. However, the environment is huge, and it would be very difficult for us if we do not approximate environment in any way. And this is exactly where our tree helps us, our magic book. So the environment, the player 2, chooses a path in this tree and a certain action for a predicate on the state. And then let's say this is our whole state space here somehow. And we know that we are somewhere here. So then as a player 1, our actions would be either we say that, okay, we take this advice, we take this suggestion. So we take action A. And in this case, we receive a reward 1. And we transition to another state space somewhere here, which is different. Or we reject this suggestion and we take some other action. In this case, we receive the reward 0. So this way, we are motivated as player 1 to follow the magic book as closely as possible, unless it's not possible for correctness of our controller. And here in this figure, what I wanted to show is an example where we set another property for our control synthesis after designing this game, the property that was not there when deep reinforcement learning agent was trained. In this case, this property is that the controller in the taxi has to come back to a gas station before the gas runs out. So let's say every 30 time steps, it has to come back. And we also put this wall here, the wall that the controller, that the taxi cannot go through while collecting passengers, and the wall that was not there on the grid during training of the agent. However, what happens here, we compared what happens if the taxi is given this kind of grid, and then if it runs into the wall like this, it is just given a stop sign. It kind of says, okay, you cannot go there, choose a different action. In this case, what would happen to the taxi? It would just run around here and not know where the passengers are. So it will be safe, but it will not collect anyone on the grid. However, using the magic book and following the advice of the magic book, as you can see here, the taxi manages to overcome the wall. Why? Because it kind of intuitively knows that there are passengers somewhere around here in the grid. And eventually, it follows the advice and finds the passengers overcoming the wall. And this is a very promising direction for us as well. Okay, so now let me show you a bit of numbers. So how we evaluate such an approach? Well, first of all, we try to see, as I said, we used random forest here. And we try to see how random forest performs in terms of this collecting the passengers on the grid compared to the original agent. And we see that the performance is quite similar. And then we synthesize a control that follows the advice of the magic book. The performance is a bit lower, but it's still good performance and quite promising. And moreover, we can also collect very interesting counterexamples from this approach. So we can, for example, say, are all the passengers collected fairly? Is first passengers collected always the first, or maybe the second always collected the first? And collecting these examples, we can do secondary training of our original wizard. Okay, so now let's say we designed this controller, we deployed it in the real world. However, there's still a neural network behind it. And the problems can be that the neural network might run into completely novel cases, completely novel images or states it has never seen. And let's say we have this neural network here. It was trained to identify two traffic signs, an icy road and the cars prohibited in the area. And now it sees completely novel sign, and you would expect that it would tell us that it doesn't know the answer to this question of classification. Unfortunately, it tries to find some similarity with what it already knows and gives us high confidence that it knows this sign. While instead, it should tell us, it should warn us that this is something completely novel. And this is something that I would like to briefly outline to you in the next work, how we monitor a neural network using abstraction techniques so that we detect such novel behaviors. And this work was published in ECI conference in last year. So let's say we have the same neural network, and in principle, we don't really care what kind of signs and images are here. We just say that these are some classes, let's say orange and green. And what we are going to do, we are going to look at the hidden layer, the closest to the output layer, because it's known to be the most explainable in the neural network. And we're going to collect the output of this hidden layer together with the classification that it is there in the training data. We do this procedure offline first. So offline, we'll look at all the training input of the neural network and collect the output of the hidden layer together with whether it was predicted as orange by the neural network or the green. And you can see these points here. These are exactly the points that we collected from the hidden layer. And then we can build our monitor. And our monitor is a simple abstraction here, in this case, boxes or interval abstraction that we fit around these points. These are multidimensional boxes. Then what we do when the system is already running deployed, we can use this abstraction to monitor the hidden layer of the neural network at the runtime input and see if something falls outside the box. And this will give us an understanding whether something is novel, and then the monitor will warn the user that there was some input and you need to check what's going on. Why this abstraction is so good? Well, because first of all, the boxes are very computationally cheap. And this is a huge advantage for us when we're working at runtime. Secondly, we show that it's effective in detecting novel behaviors in the neural network when it comes to image classification. It is independent of what kind of neural network structure we have or what data we use, as long as we have access to this hidden layer. It is very also easy to integrate into other approaches. For example, to look at the threshold of this confidence here and other approaches for novelty detection. And the user can configure how many warnings they would like to receive, or maybe how often they would like to receive these warnings. So this performs really well. However, imagine the same situation, but these novel inputs come very frequently. And let's say that you have a robot that uses a neural network for perception. And let's say the goal of this robot is to monitor your pets at home. So it was trained obviously on cats and dogs, and maybe some toys that you have at home, such as cars. But then what you notice that the food of your cats and dogs started disappearing quite frequently. So you are forced to look into the neural network, to look into the robot and see whether something went wrong. And what you might find out that an image of a squirrel was identified as a dog. Well, you take your neural network and you retrain it from scratch, now with lots of images of squirrels, such that it detects squirrels. However, you notice that the situation remains. Somebody or something is stealing the food of your pets. Then you look into the neural network again, and again, you find a situation where something else was detected and not identified as novel. So you have to do the same very expensive procedure of retraining the neural network. And this is something that we would like to avoid. And I'm not going to tell you the solution now, but I will just tease you with this problem. There are approaches in machine learning that do all kinds of active learning to prevent this from happening, or online learning, stream learning. However, there are not many formal methods that work with this. And this brings me to all kinds of open problems that still exist for controllers that somehow have some learning components in them. So as we already know, scalability is a huge issue for when it comes to controllers and learning combined together. So formal methods do not really work well when it's a huge dimensionality of input. Control synthesis for partially observable Markov decision process still suffers from scalability, even though it's quite successful in certain tasks. Runtime performance together with guarantees is a still active area, which is quite open for investigation. And real-time performance of self-driving cars, unfortunately, still suffers when we would like to verify them and make sure that they're correct. And of course, what kind of assumptions we should have about this real world where we deploy in our systems are still unclear. I presented only a few solutions, only partial solutions to all these open problems here, such as formal methods with a touch of magic and outside the box abstraction technique. However, there are still many questions that remain, and these are just examples that, again, I would like to tease you with these questions to raise some discussion. For example, how can we use model checkers and counterexamples that they give us to use them for learning? And how to specify what does it mean for a counterexample to be good for learning? Or can we use statistical model checking for learned controllers? If we cannot use formal methods, maybe we can give some statistical guarantees. So these are only a few questions, and I would really be excited to discuss these questions with you. And this is the end of my talk. Thank you very much for your attention.
All right, thank you, Anna. I think we are running quite a bit late, but I think that's okay. We probably will run about 10 minutes over schedule, looks like. Any questions for Anna?
I have a question.
Yeah, Radu, go ahead.
Sure.
So when you make this out of the box abstraction, so which layers are you considering? Are they because typically the last layers are like dense layers. You have like two dense layers at the end, and they make for you the classification. So are you looking before that? So which layers, or are you looking at several layers, or is just the layer before the dense layers that give you the classification at the end?
Mm-hmm, mm-hmm. Yeah, thanks, Rado. That's an important question. So I've seen in previous works that the layer right before the last softmax layer is the one where we can get most of the features. So this is the one that would give us the best understanding of what kind of features the neural network is looking at and how the data is clustered well. But we also looked at the previous layers and combined detections from previous layers as well. It's still
but that might blow up, because I mean there are like these residual networks, that are very good on ImageNet, and they started with 16 layers, and these days they have up to 1,000 layers, so that might be probably blow up your state space.
Yeah, this is true. This is true. But we do not need to look at all the layers. So we just need some representation of what the neural network does, and usually the last or maybe a couple of last layers are enough.
And that so you can clearly say, okay, I'm out of all the boxes that I actually knew so far. So that's you get.
No, of course we also have false positives, false negatives for our monitor. Yes, but we try to minimize that. Yes.
But you can see it pretty clearly. Okay, it's not something that we have learned before. So
yes.
All right.
That's pretty cool.
There's one question in the Q&A, but I hope you can answer that offline. And with that, I'll turn it over to Raz Budik, who will